The number they give us, that maximum, the failure shear stress, that is when the material will actually fail if the shear stress goes over 100 megapascals. We want to include a factor of safety of 2.5. We need the diameter of the pin to nearest millimeter. Like I was talking about on the other day, Tuesday, we might be able to get exactly a factor of safety of 2.5 with a very specific to 4 digits how big the diameter should be. But then we go to McMaster-Carr or we go to some other supplier of pins, and we're going to see they only sell a 1 millimeter pin, a 1.5 millimeter, a 2, a 2.5. And if we wanted one that was exactly the size we wanted, it's going to be like 10 times the cost of something off the shelf. So we might get our perfect solution, but we want to go to the nearest millimeter that's going to have a factor of safety really at least of 2.5. To do this, we're going to need to find under this loading of 80 kilonewtons, what's the actual shear stress in the pin going to be. This pin is in double shear. So what we can do is if we make an internal cut just above this, this piece that we're putting the force on, and just below this, we're going to expose what the shear force is in the pin surrounding that. So again, what does that look like? I'm cutting the pin right above where we're applying that load, and right below where we're applying that load. And we anticipate that it's going to be loaded with 80 kilonewtons of force to the right. I'm only looking at shear stress right now, so I will simplify what I draw coming out of the cut. At the top, I'm going to have some internal shear force I'll call V. At the bottom, I'll assume these are symmetric. I'm going to have V on the bottom as well. Again, double shear. The top resists the force, the external force with its internal shear force, and the bottom resists it as well. If we did not have this bracket on the bottom here, then only the top would have any resistance to this. From the internal cut, we can figure out what the internal force must be that resists the external load. $80 to the right, twice V to the left. The internal shear force is then 40 times 10 to the third newtons. We know the internal shear force. We don't know, we're going to want to find the area and therefore the diameter of the pin. But first we know it fails at 100 megapascals. We want to know what stress should we design it to be able to hold. And that way if we're loading it with more than 80 kilonewtons, it's still going to not break because it won't violate the 100 megapascals. It'll just go over the design stress. The relationship, factor of safety of 2.5, is going to be the failure stress over the design stress. It fails at 100 megapascals. Therefore, we're going to design it to fail at, doing cross multiplication here, 100 divided by 2.5. So we're designing it to only be able to handle 40 megapascals. We know that the average shear stress is, we're going to then set to the 40 megapascals, or 40 times 10 to the 6th pascals. And the average shear stress we know is equal to V over A. We found the V was 40 times 10 to the third newtons. And the cross-sectional area, I erased it, but it's a circular cross-sectional area. We're trying to find the diameter of it. That's going to be pi times d squared over 4. Or if you want to find the area first and then use that area to find the diameter, that's also fine. I'm going to skip that step and go right to finding the diameter that would cause us to have 40 megapascals of stress in the pin. The diameter that will cause 40 megapascals of stress, of shear stress, is 1.13 times 10 to the negative third meters, or 1.13 millimeters. Right? The catalog we're looking in does not sell 1.13 millimeter pins. It sells, according to this, we need the nearest millimeter. So they sell a 1 millimeter pin, they sell a 2 millimeter diameter pin. Which one do we want to go with? Right, we want to go with the 2 millimeter pin. We want to think about, we don't want to round to the nearest millimeter. What happens to the stress if we go down to a 1 millimeter pin?